Hello everyone, this is Mr. Geringer again, and this is Counting Principles. Okay, let's say that you looked in your closet and you find that you have a certain number of outfits, but you don't really know how many outfits, so you wanted to count them. We could start with looking at the 5 shirts. We'll go 5, 4, 3, 2, 1. So we have 5 shirts. Once we've picked our shirts, we have to pick our pants, so that we could have 1, 2, 3 pants, and 1, 2, 3 pants, etc., all through. Once you pick maybe this shirt, you have a choice of 1, 2, and 3. And then after you choose those, you have 2 pairs of shoes, so that's 2 and 1. And this one would have 1 and 2. It can get kind of messy awfully quick, but the idea here is that you have many different choices. So you can pick the 5, 1 and 1, or 5, 1 and 2, 5, 2 and 1, 5, 3 and 1, whatever. So there's a lot of possible opportunities. So let's look at another example. Let's say we're tossing a coin 3 times, and we're going to record which each time comes up as, what the outcome is. So the first time we toss it, the choices are, of course, heads or tails. The first time we toss it, maybe we get a head, or we could get a tail. Then we toss it the second time, which could be a head or a tail. The second time for the tail side. And then once we toss it the third time, again we have a possible outcome of heads or tails. So we put all these down. It's a lot of work, isn't it? There we go. And so when we count them, 1, 2, 3, 4, 5, 6, 7, 8, we have 8 possibilities. Every time we toss a coin, we're recording them, and there are 8 possible outcomes. So now let's look at the possibility of tossing the coin 10 times and recorded the outcome. Remember when we did it 3, it made a pretty large map. When we mapped it out, imagine trying to map this out. Here's an example of what the possible outcomes are. You could have tails, heads, heads, tails, heads, so forth and so on. So if we were to map it out, we would start with, of course, our heads and our tails, and then of course we would, from that head, you could possibly get a head and a tail. From the tail, you could possibly get, and again, this part right here is the second flip. But we have, 10 flips, so this keeps going. It just keeps going. Imagine how much the map, how big the map would be at this point. Luckily, we don't have to map this out. We have what's called the fundamental counting principle, and basically this is the official definition. If you have 2 events that occur, for example, flipping the coin once, flipping the coin twice, if the first can occur in m ways, then and the second flip is n ways, so the 2 events can occur in order, then we multiply the 2 in order to get the number of possible outcomes. There's another way of describing this principle too. It's called the multiplication rule. Basically it says that if you can identify the stages, now a stage is something that you do, some type of activity. For example, flipping a coin is a stage, rolling a die is a stage. When you're spelling out a word on a piece of paper, writing one letter is a stage. If you could figure out your stages and figure out how many options are in each stage, if you multiply the stages, then you will get the number of possible outcomes. And the example of tossing a coin 10 times, if you can imagine, it's basically the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 stages. Each stage has a possibility of head or tails, so that's 2 possible stages, 2 possible outcomes. And so if we multiply all of these, My X's look funny. If we multiply all these, then we'll get the number of possible outcomes. And again, if you multiply 2 that many times, it basically comes out to 2 to the 10th. If you do that on a calculator, you'll get 1024 possibilities, which means that if we did happen to map the 10 flips, it's going to be 1024 possibilities tall. That's a lot of data, or a lot of things to write down. Okay, let's look at this example. This is Dolores, and she's a young salesman, and she has to take clothes on her business trip. So she's thinking about 3 pairs of shoes. That's 3, 4 skirts, 6 shirts, and 2 jackets. Now, if you think about these each as a stage, for example, your pants are a stage, your upper body is a stage, your shoes are a stage, jacket, such and such, you can figure out how many outfits that she can take simply by multiplying the options. So that's 3 pairs of shoes, 4 skirts, 6 shirts, and 2 jackets, which means she has 144 outfits. So what we did was we identified each stage, and then we identified what existed in each stage, how many possible outcomes. And then from there, if we multiplied the possible outcomes per stage, then we get the total number of possible outcomes. Let's look at that example again, and let's change it a little bit. So we still have the 3 pairs of shoes and 2 jackets, but let's change it up. When she looks in her wardrobe, she sees that she has skirts and slacks. Now, typically, you don't wear shirts with slacks, so she has a choice when she goes to put on her pants. She will either pick the slacks or the skirts, which means that we have to consider them as one stage. They still go on her lower leg or her legs, but they are not indistinguishable. They're a lower extremity wear. Same with the shirts and 3 turtlenecks. You don't typically wear shirts with turtlenecks, so when she looks in her wardrobe, she has a choice. She can pick a shirt or a turtleneck. So let's look at our buckets. We need a bucket for the shoes and a bucket for the jackets, and then let's put a bucket for the skirt, the leg part, and then the upper body part. So when we're looking at this, our shoes, we have 3 possible outcomes. Our jackets, we have 2. If you add the 4 skirts to the 3 slacks, you will end up with 7 options in that, for the lower body. And then 6 shirts and 3 turtlenecks, you end up with 9 possible upper body outfits. Oops. We just start multiplying them. And in the end, we end up with 378 outfits. So again, what we did was we figured out our stages. We figured out what went into each stage, and then we just multiplied them. So again, it was easy just to pick our stages, pick what goes in our stages, and then multiply them. This is a little change on the same exact problem. We still have a choice of skirt and slacks, but this time we're adding the idea that maybe she wants to wear a shirt with a turtleneck. And so we have the options, the original options of not wearing a turtleneck but wearing a shirt, or wearing the turtleneck and not the shirt. But then we're adding an additional twist to it. If you can remember the idea of a mapping, when we were mapping the flipped coin, you pick your blouse, and then from that you pick your turtleneck. This is another application of the multiplication rule. That's why we have to multiply those possibilities. And then when you add them all up, you get 27 possible outcomes for the upperwear. Again, we have to determine what goes in this particular bucket. We added one more piece, though, is that if she wears a shirt and a turtleneck, then she's definitely not going to want a jacket. So we added the idea of she could pick her one jacket or her second jacket or no jacket. When we get done here, so we've identified what goes in each stage. And so the only thing left for us to do is just multiply them. And in the end, bless her heart, she's got 1,700 choices to make. That sounds awfully painful. So let's say that we had 5 candidates and they're running for an election, and the election results are going to come out to name the president, vice president, and secretary. So think about what the buckets are. What are your stages? I'll give you a second to think. Well, it's actually on the slide, right? So there are three stages. One's president, one vice president, and one secretary. So what are the possible, we figured out our stages, so we need to figure out what goes in each stage. So whenever the votes are tallied, how many possible outcomes for a president? Well, since there are 5 candidates, any of the 5 can be a president, right? So we know that there are 5 possibilities for president. But once a person has become president, they can't be vice president. So once we've chosen, like let's say that the possibilities here are A, B, C, D, and E, and let's say we picked A. Once we picked A is no longer available, right? Because once, if you're president, you're not going to be the vice president. So for what's left over is 4 for the vice president position. So let's say we pick B for that, which leaves 3, that's an E, 3 possibilities for secretary. Again, we've figured out our buckets, we figured out what goes in each one, and then when we multiply it, that's 20, 60. There's 60 possible combinations that we can do this, president, vice president, and secretary. Computer passwords consists of your characters, whatever they happen to be. Every time you press a character, that's an idea of an activity. So that would be a stage. So if we have 5 capital letters in our password, then we know that we've got 5 stages. 3, 4, 5. So the question is, how many letters per stage? How many options? Well, it's A through Z, and everybody knows there's 26 possible outcomes if you had a choice between A and Z. The next one, and by the way, when you look at this problem as is, it doesn't mention no duplicates. So the assumption is that we can have duplicates, which means once we pick A, we're able to pick A again, which means that the possible options for the second bucket is 26, and the third bucket is the same. Because like I said, you can continue to pick A's. That's not a very good password, but A is possibility. So now if we multiply these out, we'll get the number of possible passwords in this system. Let's take a look at the one below. Again, we have 5 buckets. The question is, how many passwords are there if we can't repeat? Which means once you've picked A for the first one, A is no longer available. So we've got 26 times 25. That's a 5. Can you believe it? Ugh. 24, 23, 22. If you multiply these out, then you'll get the number of possible passwords if there are no repeating letters. Let's look at another example. If we have a license plate, it has 5 alphanumeric characters. So again, if you, for every letter in your word, in this case a license plate, it's a stage. So we know that we're going to have 5 alpha characters, or alphanumeric characters, to fill our spots, our stages. And by the way, alphanumeric, it refers to characters that can be either numbers or letters. And that's where you get the A through Z or 0 through 9. So we've figured out our buckets, our stages. Now we have to figure out what goes in stages. So there are 26 letters that could be in there. So this could be A through Z. Or it can be 0 through 9, which is 10 possibilities. So that's 26 plus 10, so the possibilities are 36. And since it doesn't mention any idea about duplicates, we know that duplicates are possible in license plates. So each stage would include 36 alphanumeric characters. You multiply these and you can now figure out how many possible license plate numbers there are. Alright, let's look at another example. Here we have a French restaurant that serves several different possible options. On Monday, they put some options together for a fixed price dinner, and they, maybe they discount it, whatever. But the question in this particular problem is, how many possible fixed price dinners are there on Mondays? So the first thing we have to do is we have to identify the stages. If you were thinking that the stages are the red up above, so there's 5 stages, that's not necessarily true. Read the question again and figure out what it's asking and what stages you have relevant to the question. So it's basically asking the fixed price dinner possibilities, and on Monday the fixed price dinners have a possibility of an appetizer, a soup, a main course, and a dessert. Salads aren't listed. So there's not 5 stages, there's simply 4. And now we need to figure out what goes in each stage. So we're looking at appetizers. There are 5 possible appetizers. There are 2 possible soups, 7 main courses, and 3 different desserts. Multiply all of these, and you end up getting the number of possible fixed price dinners. So that's 10 times 7, 70 times 3, 210 possible dinners. In the case of a race, let's say that we've got 6 runners. They're running, assume there's no tie. They're all going to come in first, second, third, fourth, fifth, and sixth. How many stages do we possibly have? Well, there's 6 runners. 2, 3, 4, 5, 6. So there's 6 runners. How many runners is it possible to get first place? There's 6 of them, so any of the 6 could get first place. Once they've gotten first place, though, that's their spot. They're not going to be second, third, or fourth, which means they're not available to be second. And then once those 2 have been chosen, they're not available to be third. And once those 3 are chosen, they're not available to be are the lesser ones. So here is the number of possible ways that our race could be completed, which happens to be 720 possible outcomes. And congratulations, we have reached the end.